All right, so April, take it away.
Hello, everyone. Thank you all for coming. So I'm excited to tell you today about the research I've been doing, like you said, the last few years on investigating the role of resistivity and viscosity in the Sawtooth cycle. Hopefully by the end you will know what that means. So before I dive into my talk, I want to thank some people. First of all, I want to thank Dr. Craig for being my advisor for my whole time here and guiding all this research. He's been a great mentor. Also thank you to Dr. Diedrich and Dr. Bishop for being on my committee. I want to acknowledge and thank Dr. Craig Jacobson and some of the other scientists at University of Wisconsin-Madison who helped me with my research and taught me how to use all the computer simulations that I've used. I couldn't have done my research without their help. I want to thank Roland Hesse and David Martin, who graduated a few years ago from this department and did preliminary research that I've built upon, especially Roland Hesse. You're going to hear about some of his work today. And then I want to thank all the organizations that have funded this research so that I could do it and earn a little bit of money along the way sometimes. So the Department of Energy, the Alumni Association, the department, and the dean. So, yes. So first I'm going to throw you with a little summary of what my main research question has been and my main results. If you don't know what all these words mean, I'll explain them as we go along, but just to kind of have a framework in your mind of where we're going. My primary question was to look at how resistivity and viscosity affect the behavior of magnetic waves in a certain type of plasma configuration called the reverse field pinch. So in this plasma, these waves appear and decay. And we found that increasing resistivity, which is electrical resistance basically, causes the waves to grow and decay at a faster rate and reach a higher maximum amplitude. And then increasing viscosity has the opposite effect. The waves grow and decay at a slower rate, reach a lower amplitude, but viscosity seems to be less important in influencing these waves than resistivity does. So again, I'll dive into those more as we go. So where I'm going to go with this talk, first I'm going to give some physics introduction to what's motivated this research, where it fits into the picture of plasma physics and what drove our questions, and then embellish the research question that I just gave you, kind of dive into a little bit more of the specifics of what I'm looking at, and then tell you about the tools that I use to do the research. Then I'm going to go back and tell you about work from Roland Hesse, who started this research looking at average resistivity and viscosity in the plasma. Then I'll go into what I did to build on that, looking at resistivity and viscosity profiles, how what I did that was different than him, and what results I found. Then I'm going to get into a little bit of analysis of what those results mean. What do they tell us about the Sawtooth cycle as a whole? So, going into some of the physics. So first, big picture of plasma physics. So plasma is the fourth state of matter. It's ionized gas. It's found throughout the universe. It's what stars are made out of. It's what's in these light bulbs above you. And because it's a part of nature, we want to study it just to learn more about nature. It's cool science. And so that's one of the reasons why we study plasma physics. But there's also applications to plasma physics. One of the biggest that scientists are working on now is fusion energy. If we could create fusion energy as a reliable energy source, it would be clean and efficient and really be beneficial to many parts of the world. And so my research kind of fits into both of these big picture categories for plasma physics. And so that's why it's interesting, but it's just a little tiny piece. So now I'm going to dive into the more specifics of the plasma physics that I'm working on. So there's many ways to confine a plasma. Confining a plasma is controlling basically where it is in space, and you do that using a magnetic field. And in the plasma configuration that I'm doing research with is called the reverse field pinch, or the RFP. It's a toroidal plasma configuration, so the plasma is in a giant donut shape. And it's confined by a helical magnetic field. So these black lines on this picture show the direction of the magnetic field at different radii. So in the center of the plasma, it's completely toroidal, going the long way around the donut, and it gradually changes until it's completely poloidal, going around the cross-section of the donut. And then at the very edge, it reverses direction slightly. So this is the plasma configuration that I've been working with. And in these plasmas, these waves appear in the magnetic field that interfere with the confinement. These waves are referred to as modes, so the rest of the talk I'll be calling them modes. If you hear modes, think waves. And these waves are 3D, and you can break them down using Fourier decomposition into their colloidal and toroidal components. And when you refer to the modes, you refer to them using the colloidal and toroidal mode number. So that's basically the number of wave crests in the colloidal or the toroidal direction. So n is the number of toroidal wave crests. So here's a diagram of the 0,7 mode. So it has 7 humps if you go the long way around. And then m is the number of crests in the colloidal direction. In this case, m equals 0. It's a constant amplitude all the way around. So these waves fluctuate. They grow and decay in a process known as the Sawtooth cycle. So in the plasma, resistive diffusion causes current in the center of the plasma to increase. So it forms a gradient that you can see in the red curve there. And that current gradient causes unstable modes, especially ones with the m number of 1, to grow in amplitude. And then those unstable modes that are growing couple with more stable modes, such as m equals 0, and cause them to grow. And as those modes grow, they feed back on the current and cause the current profile to relax back down to that blue shape there on the left. And then the modes relax and crash in amplitude, and then the cycle starts over. So this is a diagram of one of the modes during the Sawtooth cycle. So there's time for resistive diffusion, and then the mode grows, and then it decays. And then it grows and it decays. And it's called the Sawtooth cycle. And if you look at this graph, it kind of looks like the teeth of a saw. So I mentioned that the current influences modes, and then modes influence each other and cause each other to grow. So there's 2 types of coupling that are going on. The first is we refer to as quasi-linear coupling, which is coupling between the current and the unstable modes. So for example, m equals 1, n equals 6 mode is unstable, and it couples with the current and grows through that coupling. And then it drives stable modes, such as m equals 0, n equals 1, to grow through a process of nonlinear coupling. In nonlinear coupling, 3 waves interact together. The waves that interact follow this sum rule, where the m number of each mode of 2 modes add up to the third, and the n number adds up to the third. So in this case, 0 plus 1 is 1, 1 plus 6 is 7. And so those rules guide what modes couple together in nonlinear coupling. And then as those modes grow, they feed back on the current. So the 0,1 mode, so this mode, is the largest m equals 0 mode because it couples nonlinearly with every mode that has the same m number but adjacent n numbers. So m equals 1, n equals 6, m equals 1, n equals 7. You could have m equals 1 equals n equals 7 and m1 and 8. So it couples with a lot of different modes. And so it's really important in the Sawtooth cycle. And so if we can study and understand the behavior of the 0,1 mode, that can teach us a lot about the Sawtooth cycle as a whole. And so that's why my research focuses on looking at the 0,1 mode. So there's many parameters in the plasma that influence the rate at which these modes grow and decay. But the parameters that I'm most specifically looking at are resistivity and viscosity. And we're specifically looking at how they influence the time it takes for the modes to grow and decay. So the rise and fall times. And then I'm going to look specifically how dissipation is the term for both resistivity and viscosity. How does dissipation in certain regions of the plasma matter more than dissipation in other regions? Is it just the average dissipation value that matters? We'll dive into that. And then eventually we want to know, why does resistivity and viscosity have any empirical effects that we observe? And so what is the underlying physics going on? So those were the questions driving my research. I did the research using these experimental and numerical tools. So all my research was done in connection with University of Wisconsin-Madison. They have a large RFP experiment called the Madison Symmetric Torus, or the MST. But it's very difficult in the experiment to control resistivity and viscosity independently, to set it to a specific value. And so most of my work was actually done in a simulation code known as DEBS, which looks like an acronym, but it's not. And DEBS runs based on a model of the plasma called viscoresistive magnetohydrodynamic, or MHD model, which is it's a simple model for a plasma, so it's very good for numerical codes because it runs in efficient time, but it is complex enough to predict sawtooth, and it's been shown to describe behavior very well. So it's a reliable model, and so that's why DEBS was appropriate for my research. It uses the model and runs the simulations by solving these MHD equations up here. So this first equation is mass continuity. So basically, at a given point, the amount of mass that flows in has to equal the amount of mass that flows out. It's pretty basic. The second equation is Newton's second law. So mass times acceleration is equal to force. Some of you in intro have just learned about J cross B and the force of a magnetic force on moving charge, and then this is force due to viscosity. And then the next the next three equations are all Maxwellian equations, so Ohm's law, Ampere's law, Faraday's law. So these equations are what the code solves in order to predict what's going on in the plasma. And it's very easy to adjust resistivity and viscosity and lots of other plasma parameters in the code. And so that's what I did most of my research in. So now I'm going to start telling you about what the research actually was and what some of the results were. So I'm going to go back to talk about what Roland Hesse first did a couple years ago, looking at average resistivity and viscosity. So there's these two parameters in the code that can be used to change resistivity or viscosity. The first is called the Lundquist number, and it's related to resistivity. So the definition of the Lundquist number is that S is equal to the resistive diffusion time over the Alfvén time. If you want to know what that means, I can explain it more later. But what's important to know is that the Lundquist number is inversely proportional to resistivity. So by increasing the Lundquist number, Roland was able to look at how decreasing resistivity influenced plasma behavior. The viscosity he changed using the magnetic Prandtl number, which it is proportional to viscosity. So by increasing the Prandtl number, he increased viscosity. So he did lots of different DEBS runs with different Lundquist and Prandtl numbers, and then he compared the average rise and fall times. The way he did that was he let a run go for many sawtooth. He averaged all the sawtooth of the run together into one sawtooth, and then he quantified the rise and fall time as the time between half height to full height, or full height to half height when it was falling. So that's how he compared his runs. And when he did that, he found that increasing the Lundquist number caused the rise and fall time of the sawtooth to increase. But if you remember, Lundquist number is inversely proportional to resistivity. So that means that increasing the average resistivity in the plasma caused the rise and fall time of the 0-1 mode to get shorter. So it grew in decay faster. And you can see that fall time, there is more influence on fall time than on rise time. For viscosity, we see a similar effect. Rise and fall times both increase again with Prandtl number, but this time Prandtl number is proportional to viscosity. So actually viscosity and resistivity have opposite effects on the rise and fall times of the 0-1 sawtooth. So increasing viscosity causes the rise and fall time to get longer. But again, we see that there's more impact on the fall time than on the rise time. And it's a little hard to see on the graphs, but the actual scaling with the viscosity is less than the scaling with resistivity. So he sees that resistivity is more important on sawtooth behavior than viscosity. Now these are great results, but again, they're all in a simulation that's based on a model. So we want to make sure that this is accurately depicting what happens in the experiment. And so I did some comparison with experimental data from the MST. Dr. Craig Jacobson at University of Wisconsin-Madison collected some data and sent it to me, and I averaged it together using the same method that Roland used and quantified the rise and fall times so that we could compare. Now the actual Lundquist number in the experiment tends to be higher than the simulation, and that's because in the simulation, the higher the Lundquist number, the longer the computational time necessary to run the code, and so it's not very practical to run the code at the same Lundquist number as the experiment. But if the code is predicting what would happen in the experiment, the trend that we see between rise and fall times and Lundquist number should agree. And you can see on the left that for rise time, the trend is pretty constant. The experimental and simulation data is agreeing, but you can see here on the right that the fall times, there's a big discrepancy here. So that begs the question of why. It could be that the model we're using is not sufficient to fully predict and explain all of the sawtooth behavior. But there may be explanations that are maybe less drastic. It could be that there's parameters that are accounted for in the simulation, but that we're setting to different values than they actually are in the experiment. And so maybe that's what's causing the discrepancy. And so one of those parameters that could be different is the actual dissipation profiles. So maybe it's not just the average resistivity or viscosity that matters, but resistivity or viscosity at specific locations in the plasma. And so now I'll tell you about what I did to look into that question. Do dissipation profiles matter? There's lots of different dissipation profile shapes you could use. You could increase the resistivity at the center of the torus, at the edge, somewhere in between, multiple places. So, I mean, you could just try thousands and thousands of profiles, but we try to go about it systematically, and so we use this concept of mode resonance to decide what dissipation profiles to test. So mode resonance occurs when the 3D structure of the mode, so remember a mode is a 3D wave, so when the 3D structure of the mode matches the helical structure of the magnetic field, that will occur at a certain radius, and at that radius we say the mode is resonant. We figure out where resonance occurs using this parameter called the Q profile. So the Q profile tells you how helical the magnetic field is. It's the ratio of the number of toroidal turns in the magnetic field to the number of poloidal turns. When Q is equal to the poloidal mode number over the toroidal mode number for a given mode, then at that radius, the mode is resonant. The structures of the field and the mode match. And so here is a graph with the location of resonance for several different modes, at a couple different times during the sawtooth crash, and you can see that m equals 0 resonance lies in the outer third of the plasma. And so that is, and so there's, it's likely that the mode is most affected by dissipation in the region where it is resonant. And so we decided to first test profiles that varied the resistivity or the viscosity in the outer third of the plasma near m equals 0 resonance. So here are the resistivity profiles that I used. So I started with a polynomial curve, that pink curve there, that kind of has a spike in the resistivity in the edge. And then I added a hyperbolic tangent shape to basically add a plateau of resistivity to either add or subtract it. To kind of help you know how to interpret graphs later, the naming system that I use for these profiles, P means that dissipation is being added, N means it's being subtracted, it's negative. And then the numbers next to it are basically the relative amount of resistivity in that region. For viscosity, the profiles were very similar, but this time the initial polynomial I started with was steeper, and I also had this inner polynomial curve that stayed the same for all the profiles. The reason I made those adjustments for viscosity was because of the issue of numerical convergence and stability. So for a numerical code, in order to know that your results are reliable, the run has to be converged. So convergence means, well, let me backtrack. When you run a numerical simulation, you have to discretize a continuous system into a certain number of points and solve the system at a certain number of points. And the resolution is how many points you're using to solve. And so convergence means that the resolution is sufficient to get a solution that reflects what would actually happen in a continuous system. And you know that there is convergence if you increase the resolution and the results stay the same. When I did my first runs, I wanted to make sure they converged, so I increased the resolution and the results changed slightly. So I was like, okay, well, they're not converged. So is there anything else we can kind of use to help figure out if a run is converged or not at a specific, like is this higher one that I just ran it at, is that converged? So then I looked at the numerical stability. So instabilities are basically amplification of any round-off error or noise that's happening as the equations are being solved. And it results in some jagged spikes in curves that should be continuous. So like this is a numerical instability that I found in the radial velocity profile. And numerical stability and convergence are not identical, but if I could remove these instabilities, it was very likely that I reached convergence. And so I was able to remove the instabilities by increasing viscosity in the regions where it was unstable. So there were some instabilities near the edge and some at the center near r equals 0. And so that's why I had a steeper viscosity curve at the edge and I had that added viscosity curve in the center. And so those remove the stabilities, and so I used those profiles, and then I ran the runs with 320 radial points, 6 colloidal mode numbers, and 171 toroidal mode numbers. So that's what I used to do all of my runs. Now, if you remember what Roland did, he let the runs go for a long time, averaged together all the Sawtooth, and quantified the rise and fall times. For my runs, it was very difficult to do this because sometimes the profiles just caused the system, because they were such extreme resistivity or viscosity values, it caused the system to get maybe a little wonky. It was difficult to get consistent Sawtooth that I could average together and really compare to other runs. It also took a very long time. And so I used a feature of Debs called restart files to do my runs. So Debs, at every certain number of time steps, will produce a file that contains all the information of a run. So if you used the file and didn't change anything else and started the run from that file, it would just keep going as if you'd never stopped it. So I used the restart files, but I changed the resistivity or viscosity and then used that to do my runs. So I took a restart file from, I ran a run with the basic polynomial resistivity and viscosity. Then I took a restart file from right before the first Sawtooth of that run and did all my subsequent runs from that Sawtooth, just changing the resistivity or viscosity profile. And my primary method of analysis was to visually overlay this first Sawtooth in all of the runs and compare the relative slopes of the rise and the fall in order to visually see what's happening to the rise and fall time. So I did that for rise time first, and in these graphs, the height of the Sawtooth is normalized so that you can really see the relative slopes. And you can see on the right, remember N100 is the least amount of resistivity and P100 is the most amount of resistivity. That as you increase the resistivity near m equals 0 resonance, the curve is getting steeper and steeper, meaning the rise time is getting shorter and shorter. For viscosity, you see the opposite effect. The rise time is getting longer and longer as you increase viscosity. But the difference between the longest and shortest viscosity one is a little bit less than resistivity, so we kind of see that viscosity is having a weaker effect than resistivity. We see a similar thing in fall times. The fall times were a little more wonky, but you can still kind of see the same basic trend that as you increase resistivity, the fall time gets shorter. As you increase viscosity, the fall time gets longer. Viscosity again seems to have a weaker effect than resistivity, but the total variation in fall times for both resistivity and viscosity is more than it was for rise times. So if you look at the total variation in fall times here, compared to how much the rise time is changing, there's more effect on the fall time. Now maybe some of that's kind of sounding familiar, because that's basically the same thing that Roland was finding. So he found that increasing average resistivity caused rise and fall times to decrease. I found that increasing the resistivity near m equals 0 resonance caused the rise and fall times to decrease. And viscosity had the opposite effect in both cases, and also a weaker effect for both average and profiles. And the fall time scaling was stronger in both cases. So you can see the slope there on the right is steeper than for rise time. The variation here is greater than the variation here. So my results seem to be agreeing with his, so that's a good sign that I'm on the right track. It also is perhaps suggesting that our hypothesis that resistivity and viscosity near m equals 0 resonance is most important for influencing that mode if the behavior we see with average resistivity is reflected in the profiles near m equals 0 resonance. Now there's more that changes besides just the rise and fall time. So these are non-normalized amplitudes of the first Sawtooth, the whole first Sawtooth rise and fall. And you can see that, especially the resistivity one's a little crazy. It's easier to see in the viscosity one, that as you increase viscosity and rise and fall time increases, the amplitude of the Sawtooth decreases, and also the total duration of the Sawtooth crash increases. For resistivity, as you increase resistivity, the total duration decreases as rise and fall time decreases, and the maximum amplitude increases. So those were the empirical results with resistivity and viscosity that Roland and I found. But what do these mean? Why are these effects happening? Why do resistivity and viscosity matter? What role do they play in the Sawtooth cycle? And so there's lots of questions associated with that. But I started to dive a little bit into one that I'm going to tell you about, which was looking at the rate of energy flow in and out of modes during the Sawtooth cycle. So in a paper by Ho and Craddock from 1991, they analyzed the Sawtooth cycle by looking at the power flux, or the rate of energy flow, in and out of the mode throughout the Sawtooth crash. And they broke the power flux in and out of a mode down into 4 components. So the quasi-linear component is the energy in or out of a mode due to coupling with the current. The nonlinear term is the energy in or out of a mode due to coupling with other modes in that 3-mode nonlinear coupling I told you about in the beginning. And then the resistive and viscous fluxes are the energy in or out of a mode due to resistive dissipation or viscous dissipation. And so the sum of all of that will tell you the total energy in or out of a mode. When the mode is growing, that total energy will be positive because it's energy flowing into the mode. When the mode is decaying, that value will be negative as energy flows out of the mode. So because I was looking at resistivity and viscosity, I decided to first look at the resistive and viscous flux and how changing the resistivity and viscosity profiles changed the resistive and viscous flux out of the mode. And we found that the resistive flux shows an inverse correlation with rise and fall times. So I'll unpack what that means. So the top here are graphs of the level of resistive flux during the first sawtooth of every run. And the bottom is the graphs that you saw earlier of the sawtooth and the magnetic field. They're a little crazy, but these graphs are aligned at the same point, and so you can kind of see that the resistive flux is spiking in magnitude as the sawtooth is spiking, and the total amount of time that the resistive flux is high is the same amount of time that the sawtooth crash is going on. And you can see, so for example, for resistivity of the green curve, the runs where the rise and fall time were shorter and had higher maximum amplitude. And so the higher resistivity, there were greater peaks in resistive flux. So as the resistivity increased, there was more resistive flux out of the mode, and that correlated with a shorter rise and fall time. For viscosity, you see the opposite effect going on. As the viscosity increased, the amount of viscous flow out of the mode decreased, and that corresponded to an increase in rise and fall time. And so resistivity and viscosity have opposite effect on resistive flux and the opposite effect on rise and fall times, if that makes sense. And so there's an inverse correlation between the resistive flux and magnitude and the rise and fall times. And I expected to see a similar thing with viscosity, maybe the opposite, but I didn't. There was not a consistent correlation between the level of viscous flux and the rise and fall times. The viscous flux shape looks different than resistivity. The peaks are much sharper, but the location of the peaks still corresponds to the peaks in the sawtooth. And we find that the magnitude of those peaks in flux increase as you increase either resistivity or viscosity. So resistivity and viscosity both have a similar effect on viscous flux, but opposite effects on rise and fall times. So there doesn't seem to be a consistent correlation there. So again, that begs the question of why? And in fact, why does resistivity affect the amount of viscous dissipation out of a mode at all? Why does viscosity affect the amount of energy lost through resistive dissipation? That didn't make sense to me. And so that kind of indicates that resistivity and viscosity are doing more than just causing energy to be lost out of the mode the whole time. It also is likely influencing the rate, for example, that energy is flowing between the current and the modes, or the rate that energy can flow between modes that are nonlinearly coupled. And then that indirectly affects sawtooth behavior, and as the sawtooth amplitudes and other aspects of behavior change, then that changes how energy flows out of the mode through resistive and viscous dissipation. So in order to understand that, we need to look at these quasi-linear and nonlinear flux terms. Unfortunately, right now, my code that solves these equations, there's indication that it's not solving them correctly, and so I haven't done that analysis yet, but that's a next step that I will be doing to hopefully really understand what role resistivity and viscosity have in the sawtooth cycle. So, to summarize my results, increasing resistivity, whether that was average resistivity or resistivity near m=0 resonance, caused the rise and fall times to get shorter, the total length of the sawtooth crash to get shorter, the maximum amplitude to get higher, and then viscosity had the opposite effect. So increasing viscosity, again, whether that was average viscosity or viscosity profiles, caused longer rise and fall time, longer total duration, and a shorter sawtooth amplitude. In both cases, the influence on fall time was more than on rise time, and viscosity seems to have a weaker effect than resistivity. When looking at the power flux in and out of the mode, increasing resistivity caused both the resistive flux and the viscous flux to increase. Increasing viscosity caused the viscous flux to increase, but the resistive flux to decrease. And so the resistive flux out of a mode seems to show an inverse correlation with rise and fall times, but viscous flux does not show a constant correlation. And so there's evidence that resistivity and viscosity are not just dissipating energy out of the mode, but are also influencing the rates that energy transfer between the current and modes, or between modes and each other, can happen. So there's lots more work to be done. The first is to check my results. So I mentioned I removed numerical instabilities, but I didn't actually confirm for sure that I have convergence. So I need to do my runs again at a higher resolution in order to check that I really have convergence. Now, before you think, well, maybe all these results are just moot, when I changed the resolution before, the trend that I saw stayed the same. So, for example, increasing resistivity caused the rise and fall times to decrease, but the amount that it increased or decreased for the case of viscosity was what changed. So to really know how important resistivity and viscosity are, I need to confirm that my runs are converged. And then hopefully figure out a way to quantify those rise and fall times so that they can really be compared to Rowland's results with average dissipation. Because my profiles are actually changing the average dissipation value in the plasma. So, like, for example, the P100 is increasing the average resistivity value that you would get. And so in order to really see how important the resistivity or viscosity near m=0 resonance is compared to just the average value, I need to find a way to quantify and compare the results. From some preliminary work that I did, it is likely that the resistivity and viscosity near m=0 resonance is causing additional effect than just the average value did, but in order to know what that effect is, you need to quantify the results. And then, though the m=0, n=1 mode teaches us a lot about the Sawtooth cycle, to get a full picture, we need to look at the behavior of other modes, m=1 modes and other modes that are involved. And then it'd be helpful to test dissipation profiles that change the levels of dissipation near other mode resonances and see what effects those have. And then these are all simulation results again, so it would be helpful to figure out how to compare all of these to experimental results. That would include MST, but also other reverse field pinch experiments, because we want to know if our results are universal. Are they universally true about reverse field pinch plasmas? So if we can compare to experimental results, that will just verify our work. And then diving into the deeper physics, I need to look at the quasi-linear and nonlinear flux terms from Holm-Craddock's paper in order to really figure out what parts of the Sawtooth cycle resistivity and viscosity play a role in. And then finally, there are many things besides resistivity and viscosity that are important in the Sawtooth cycle, including how much feedback there is on current levels, what the external circuitry conditions are that's driving the plasma. And so Eventually, we want to look at all of these parameters in order to really get a full picture of how the Sawtooth cycle and the reverse field pinch plasmas behave. So, thank you for listening. Are there any questions?
I have a couple of what are basically chicken and the egg questions.
Mm-hmm.
You mentioned this level of current feedback, and you're going back and forth between kind of comparing experiment results with theory, right?
Mm-hmm.
But that woke me up at the end a little bit because, like, wow, if your instrumentation is kind of suffering or experiencing kind of an enhancement, it sounds like. Is that correct?
Perhaps.
Yeah, like wow, right? So how do you kind of isolate and go back? I mean, I guess what
Yeah.
how is that influencing?
So in DEBS, you set the conditions of what the external circuitry would be if this was an experimental plasma. So you can say this is what the external electric field is, this is what the external magnetic field is. And so then you would hopefully set those to parameters that match with what you're doing in the experiment, and then you can see how that works. So that would be a way to compare those without actually changing them in the experiment as well. You could actually do those tests in the simulation.
That's great. And then, I see Maxwell's equations, right, show up and everything. It seems like there's a very strong assumption of these fundamental expressions to describe what's going on, right?
Mm-hmm.
And this is where I'm so much an outsider. What is the level of confidence that those expressions are kind of the thing, and that there's not
Right.
missing portions that you aren't really accounting for?
Yeah, well, I guess it depends what aspect of the behavior you're talking about. For the Sawtooth cycle, we don't know for sure that the Sawtooth behavior is being predicted fully and completely. That's one thing we're trying to figure out. If we can explain, so going way back to the beginning, if we can explain the discrepancy we saw in like the fall time graphs here,
Mm-hmm.
if we can explain this by changing other parameters in the simulations, then we could say, okay, maybe the model is okay. But if we keep trying things and are never able to explain this difference, then that would suggest, okay, this model has weaknesses. There are other models of plasmas, and they all have different strengths and weaknesses. But a lot of them are very difficult to do in reasonable computation time in a numerical simulation. And especially looking at behavior as crazy as Sawtooth. And so in lots of other past work, there's lots of evidence that this model describes the behavior well, predicts Sawtooth. Some models don't even predict Sawtooth, so it does that. So there's lots of evidence that this is a good model, but we really want to see how maybe we will reach a point where it's not good enough and we need to go to a different model. But maybe we won't. So.
I'll ask another.
Go for it.
You have a gut sense of where your data is falling. You said you haven't really quantified rise and fall times yet, or you're working on it. Do you have like first, is there an accepted way in your field to quantify the rise and fall times that you've gotten from your simulations? And then secondly, are you kind of mapping out for yourself where those are falling on those two figures?
Right. So rise and fall times isn't really something that's been studied much before. So the only before that at least I know of right now is what Roland Hesse did. And I will hopefully figure out a way to do that with my runs. Again, the Sawtooth are more difficult to average than Roland's were, but maybe I can adjust the behavior slightly and reanalyze his in a way that matches mine. But hopefully eventually there will be a way to do that. As far as where mine fit on the graph there, so the problem here is that the fall times are too long compared to the experiment. And when we increased the resistivity a lot, the Sawtooth falls got really short. Let's see. Here, so like these Sawtooth falls are much shorter, especially when you increase resistivity a lot. And so there's evidence that we have found a way to move these data points down. Whether it's enough yet, I can't say, but there is evidence that it's moved it down. And there's also evidence that the profile results that I found, that once I quantify those, that the resistivity viscosity near m = 0 resonance does matter more than the trend that we just see from average dissipation.
Do you have any concerns that you've chosen like 5, profiles, right? Do you have any concerns there's any kind of like thresholding effect that you might be missing, or do you expect this to be kind of continuous behavior and your 5 points are well selected kind of thing?
Well, that's a good question. I mean, we see the trend that seems to flow consistently between those, and maybe if we tried other profiles in between, we would fill in the gaps, and maybe that would be further work to do. But the main point was to see that as like you increase the level or decrease the level, if that matters, and we're seeing a consistent trend, so I think it is reasonable to use the profiles that I used. So. Yes?
So is this a one-dimensional, two-dimensional, three-dimensional simulation?
It is a...
Think hard. You know the answer to
Yeah, I
this.
do know the answer to this.
Think about your resolution.
It's a three-dimensional system. Yeah, so, oh yes, it is three-dimensional. So it's a torus, but it's approximated as a periodic cylinder. So it's cylindrical geometry. So we have the radial direction, the theta direction, and the z direction.
Yeah. You had like something like 300 points radial?
Yeah.
That's what you said.
Yes. Oh, that's not
Well,
here.
yeah, so
Yeah.
300 radial points that is outwards, and then toroidal points around and going this way.
Yes.
Do you think you maybe understand that sort of stuff?
So I think the way it works for like the poloidal and the toroidal, I don't fully understand how that works, but I think it's more, I don't fully understand how that works, but I picked this, the resolution based on advice from Dr. Craig Jacobson and other people at Madison, what they've used before that works well. So maybe to check convergence, I also need to not just change. So when I was checking convergence before, I was just changing the radial resolution. Maybe I also need to check the poloidal and toroidal resolution as well. But there is, a lot of people have used this resolution before, and it works well. So with my crazy profiles, sometimes you need higher resolution, so that's something I need to check.
I guess comment that Debs works in a spectral sense for the poloidal and toroidal direction, so it does it in terms of mode numbers, not spatial points. And if you look at the spectra, they drop like a rock actually for both of those. So you can you capture enough modes to kind of capture most of the spectrum, and then some get ignored. And like you say, you should check.
Yeah,
that changing those
too.
numbers doesn't change anything.
Mm-hmm.
But the sense is that this is probably good enough by looking at the spectrum.
Do you all do any cluster computing or?
Yes. So maybe the simulations were run at computers at University of Wisconsin-Madison, on a computer cluster up there, computer bank up there.
But it's not parallelized.
Yeah, it's not a parallel.
They've made a parallelized version. You get like a factor of 2 speed up, so it's not huge.
Yeah, it doesn't seem like with what you're doing you can get much improvement, but maybe with the number of cores you can.
She has lots of jobs in parallel, so she'll do like different resistivity.
Yeah, so I can run all the
Right.
runs at the same time.
Yeah.
But for a specific run to go along, I have to wait. Yeah.
I'm happy to say that I actually don't even know how to submit a job. After all these students doing these things, I still have never done one myself. It's so great.
Oh, you're gonna do now with it.
I don't know. You wanna come work?
You have to learn at some point.
Yes.
Next person, thank you.
So this field of research seems like it's big, and then you picked it up from Roland, and I'm sure he's talked to Dr. Craig and got things. Do you have any advice for like going into research that's been started by someone else and picking up people left off, like how to catch up and move forward?
Well, first advice for someone who, especially at a place like here, who you know someone else is going to be doing the research after you, is try to leave good notes. I admit I haven't done this well, so hopefully before I leave I can do this. But when I was picking up on Roland and David Martin's work, they left notes on like how to run the job, since Dr. Craig doesn't know, and like they and they left comments in their code and stuff so that I could kind of follow. But I guess the biggest advice would be patient and look around through all of their files. Maybe there's some hidden instructions that you don't see at first. Don't be afraid to ask questions, ask Dr. Craig. And for me, I asked Dr. Craig Jacobson and a lot of other people, or a couple other people up there, questions on how to run Debs and what resolution to use and things like that. So I'm trying to think if there's any other advice from that.
Do you remember the first thing that you did with the code?
The code?
Your first summer, one of the first projects that you had, I think relates to this question a little bit.
It was to try to re-get what Roland got right, yeah. So you can use their results as kind of guiding that you're on the right track. If you can reproduce their results, then that tells you, okay, I'm doing this right. Now what can I do to change and get more results? I had something else I was going to say.
It's nice because in the process you also fixed a few little things that weren't quite right with most.
Yeah.
How much time did you actually spend in Madison?
Madison? Not very much. We went up there a couple times my first summer for like a day.
Yeah.
And yeah, I think the first day we went up, I met with Dr. Craig Jacobson for an hour or two to get some advice. But since most of it was all computational, I just emailed a lot with him, with the people running the computer block, and so most of it was through email. We went up a couple other times, though I think most of that wasn't actually for my research. I just kind of tagged along for other people. And then we did a conference call once to share our research and kind of get advice on where to go from there. We did that at the end of the summer, my first summer. Since then, there's been less communication, I think, just because, I don't know, we're moving along, and I think Craig Jacobson has left Madison, and so, yeah.
Okay. Did you actually get to see the
MST?
Mm-hmm.
Yeah, we should. Dr. Craig gave us an extensive tour. Very overloaded information the first day.
Yeah.
The subsequent visits internalized a little bit more. It's cool.
Yeah, I went to the grad school that I went to in Switzerland has a tokamak plasma reactor.
Mm-hmm.
So I don't know. Do you know what the difference is between a tokamak and an RFP reactor?
Let's see. I don't remember everything. I think because you can have a toroidal tokamak too, can you? Yeah. So you can also have like spherical tokamaks, but I think the aspect ratio is different. So like the ratio between the major and minor radii is different. The magnetic field that you use is different. There's so where was the Q profile? So in the RFP, the magnetic field reverses direction at the wall. I don't think it does that in tokamak. Beyond that, I'm not sure.
Thanks.
The biggest difference actually is that the tokamak field is about 10 times stronger.
Oh, okay.
Which, if you're going to run a power plant, means a lot of money gets spent on the magnetic field. So this is a possible cheaper way, but has all kinds of instabilities. So
I know that one of those has a very tall, elongated.
yeah, they have a non-circular
non-circular
cross-section.
cross-section. Kind of
Yeah,
distinctive.
like a shape of a D, for example, that's
Yeah.
pretty popular configuration.
Other questions before we switch to just committee mode?
Yes.
What has been some of the most rewarding parts of this, besides finishing your paper
Yes.
and this presentation? Which I'm sure that's rewarding, but you don't get to pick that.
Let's see. I think the most rewarding is, well, especially at the beginning, when I was changing these profiles, the runs would just like crash all the time, or they'd run and then just go into numerical instabilities and not give me any results. So once I figured out ways to get the code to go through a whole Sawtooth. That was very rewarding. The runs where I got very pretty Sawtooth, that was very rewarding. It was just like, ah, beautiful. Why can't all my runs look like this? And then one thing that's been rewarding is just as I've gone through the last couple years and as I have conversations with Dr. Craig and talking about the physics of what's going on, and as I've seen myself understand more and more of what that means, because we have no, unless the years they offer the plasma physics class, which has not happened while I'm here, we have like no background in plasma physics. And when I started, I didn't even know upper level electromagnetism. So just seeing and like being able to understand more of what's going on and really be able to actually think about the ideas Dr. Craig gives of like, oh, maybe it's this, and like know what he means and actually be able to wrestle with that a little bit instead of just be like, yeah, maybe, I trust you to know. So that's been fun. And yeah, just seeing myself more naturally think like a researcher and naturally ask questions has been cool.
Good. That's a good question to end on, I think. So
Thanks,
have you guys
Sarah.
step out for a little bit, and Ted has treats to reward you for paying good attention.